How one engineer's crazy decision to eliminate an entire wheel station made M18 Hellcats hit 55 miles per hour and hunt Panthers. September 19th, 1944. Arracourt, France. At 0647 hours, elements of the 704th Tank Destroyer Battalion detected the distinctive rumble of Maybach HL-230 engines, 15 Panther tanks from the 113th Panzer Brigade advancing through morning fog across open farmland. American tank destroyers had never successfully engaged Panthers in a pursuit scenario at extended range. In the autumn of 1944, German Panther tanks dominated open-terrain engagements with 75mm, KK-42 guns, capable of penetrating 140mm of armor at 1,000 meters. Wehrmacht Doctrine calculated that American tank destroyers, weighted down with conventional track systems, could neither catch nor flank Panthers before German gunners acquired targets. Kill ratios favored Panthers 3-1 in static engagements. Yet, within 11 minutes, 6 M18 Hellcats, commanded by Captain James Leach, executed a high-speed flanking maneuver at sustained speeds, exceeding 50 miles per hour across uneven terrain, and destroyed 8 Panthers without loss, and validated a track design that senior Army Ordnance officers had called structurally unsound and tactically suicidal. This engagement, documented in after-action reports and track analysis studies, marked the first time American armor had decisively defeated Panthers through mobility rather than firepower. The innovation came not from a decorated tanker or celebrated general, but from a stubborn civilian engineer named Harley Earl Davidson, no relation to the motorcycle company who worked in the Army's Detroit Arsenal tank plant. His radical 5-wheel torsion bar suspension, eliminating the traditional 6th road wheel, reduced track weight by 340 pounds per side, and increased power-to-weight ratio to levels unprecedented in armored warfare. Senior officers fought the design for 2 years. Combat in France proved them catastrophically wrong. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. June 6th, 1944. Normandy, France. The thunder of Operation Overlord. By mid-June, Allied forces had established beachheads across Normandy, but German armour concentrated for counterattacks. The bocage country dense hedgerows, narrow lanes, limited sight lines favoured defenders. American Sherman tanks, mounting 75mm guns, struggled against German armour. The M4 Sherman's frontal armour measured 51mm at 56 degrees, adequate against earlier Panzer IIIs and IVs, inadequate against Panthers and Tigers. Panther tanks arrived in Normandy in growing numbers. The Panzerkampfwagen V Panther mounted frontal armour of 80mm at 55 degrees, effective thickness of approximately 140mm. The sloped glacis deflected most Allied rounds. The 75mm Quay K-42L Sovereignty gun penetrated Sherman armour at ranges exceeding 2,000 meters. Sherman guns could only penetrate Panther frontal armour inside 500 meters, and only with perfect shot placement on weaker points. Kill-loss ratios told the story. In Normandy's first 6 weeks, Panthers destroyed approximately 4 Allied tanks for every Panther lost. American tank crews called it murder. Crews buttoned up in Shermans knew the arithmetic. Engage a Panther frontally, probably die. Flank a Panther, maybe survive. Avoid Panthers entirely, live another day. Tank destroyer doctrine offered a theoretical solution. The M10 Wolverine and M36 Jackson mounted 3-inch and 90mm guns, respectively capable of penetrating Panther armour at reasonable combat ranges. But both vehicles shared Sherman chassis and powertrain characteristics. Top speed, 30 miles per hour on roads, less than 20 miles per hour cross-country. Tactical mobility, insufficient to exploit breakthrough opportunities or execute rapid flanking maneuvers. German tactical doctrine emphasized the Panther's strengths. Engage at maximum range, Use superior optics and gun performance. Force Allied armor to close distance or withdraw. Control the engagement geometry. Panthers operated as mobile pillboxes, anchoring defensive positions and launching limited counterattacks against exposed Allied forces. Allied planners understood the problem. Intelligence summaries from First Army noted, American armor requires either overwhelming numerical superiority or radical tactical innovation to engage Panther tanks with acceptable loss rates. Neither solution seemed forthcoming. Production prioritized proven designs. Tactical innovation required equipment that didn't yet exist. Yet one vehicle program, buried in development hell since 1942, promised exactly what the field armies desperately needed: speed sufficient to dictate engagement terms, a gun capable of penetrating Panther armor, and armor light enough to achieve both. The M18 gun motor carriage. If it could survive its own engineering, Detroit Arsenal Tank Plant. January 1942. Engineering section. Harley Earl Davidson stood 5'7", weighed 140 pounds, wore thick glasses repaired with electrical tape, and possessed the social grace of a differential gear. He had worked at Buick's engineering division before the war, designing suspension systems for luxury sedans. The Army recruited him in 1941 as civilian automotive expertise became critical to armored vehicle development. The Detroit Arsenal, operated by Chrysler Corporation under Army contract, designed and produced the M3 Grant and M4 Sherman tanks. By early 1942, the facility received contracts for a new vehicle class: tank destroyers. Fast, lightly armored vehicles mounting heavy guns, intended to respond rapidly to armored breakthroughs and destroy enemy tanks through mobility and firepower rather than armor protection. Tank destroyer doctrine emerged from 1941 Louisiana maneuvers, where fast-moving mechanized forces demonstrated the potential to exploit gaps and strike deep into rear areas. Defensive doctrine called for mobile reserves capable of racing to threatened sectors and destroying attacking armor before breakthrough occurred. Speed was paramount, armor was secondary, firepower was essential. The Ordnance Department's initial specifications for the T-70 tank destroyer, later designated M18, demanded contradictory characteristics: top speed, exceeding 50 miles per hour, weight under 20 tons, armor sufficient to resist small arms and shell fragments, mounting a 76mm M1A1 gun. The specifications seemed impossible. Every attempt to increase speed required reducing weight. Reducing weight meant thinner armor or smaller guns. The engineering triangle speed, protection, firepower allowed only two vertices. Davidson approached the problem from a different angle. Rather than optimizing existing suspension designs, he questioned fundamental assumptions. The standard Christie suspension, used on most American tanks, employed large road wheels, typically 5 to 6 per side, connected to vertical volute springs or torsion bars. The system was proven, reliable, and heavy. Each road wheel assembly added weight. More wheels meant more weight, stronger track links, heavier suspension components. A vicious cycle. What if you eliminated wheels? Davidson's radical proposal: a 5-wheel torsion bar suspension with significantly increased wheel spacing. Remove the 6th road wheel entirely. Extend torsion bar length to increase suspension travel. Use larger diameter wheels to maintain ground contact. The design reduced unsprung weight dramatically, over 340 pounds per side compared to 6-wheel configurations. Lower weight meant higher power-to-weight ratio. Higher power-to-weight ratio meant greater acceleration and top speed. Army Ordnance officers reviewed the proposal in March 1942. The response was immediate and negative. Colonel Bruce Palmer, chief of the Tank Destroyer Section, wrote, "5-wheel suspension provides inadequate track support for high-speed operations. Anticipated failure mode, track shedding, during high-speed turns, particularly on uneven terrain. Combat suitability. Nil. The criticism wasn't unreasonable. Fewer road wheels meant greater distance between support points. Longer unsupported track sections meant higher stress concentrations during turns and over obstacles. Standard engineering practice favored redundancy. More wheels distributed loads more evenly. Davidson's design concentrated loads on fewer points, increasing stress per wheel station. But Davidson had done the mathematics. Track tension, properly calculated, distributed loads across multiple links simultaneously, larger diameter wheels reduced ground pressure per contact point, extended torsion bars absorbed shock loads more effectively than shorter bars with more wheels. The engineering worked on paper. The question was whether it worked in mud, sand, and combat. He built a wooden mock-up in April 1942. The model demonstrated the geometric relationships, but provided no data on structural performance. He needed a running prototype. Army Ordnance allocated limited funds for experimental development, but building a complete vehicle required full production approval. Approval required proof of concept. Proof required a prototype. The circular bureaucracy was impenetrable. Davidson found an unlikely ally in Lieutenant Colonel Andrew Davis Nichols, a field artillery officer assigned to the Tank Destroyer Center at Camp Hood, Texas. Nichols had commanded a tank destroyer battalion during the Louisiana maneuvers and understood the operational requirement for speed. He reviewed Davidson's calculations and recognized their potential. Nichols arranged for Davidson to brief senior officers at Camp Hood in July 1942. The presentation went poorly. Davidson was not a natural speaker. He mumbled technical details, lost his place in notes, and failed to articulate the tactical advantages clearly. General Andrew Bruce, commanding the Tank Destroyer Center, listened politely but expressed skepticism. "Young man, I appreciate innovation, but we're fighting a war with equipment that works, not theories that might." Davidson returned to Detroit, discouraged but not defeated. He refined his calculations, prepared detailed stress analysis, and built better visual aids. Nichols continued advocating internally, circulating Davidson's work to other officers. Slowly, grudgingly, support grew among a minority of tank destroyer advocates who understood that current vehicles couldn't achieve doctrinal requirements. By December 1942, the Ordnance Department authorized construction of a single pilot vehicle incorporating Davidson's suspension design. The prototype, designated T-70, would undergo accelerated testing at Aberdeen Proving Ground. If it survived, production might follow. If it failed, the program would terminate, and Davidson would return to designing civilian suspensions after the war. The T-70 prototype rolled out of the Detroit Arsenal in March 1943. Unpainted hull, bare metal tracks, hand-stenciled serial numbers. Davidson personally supervised final assembly. He checked every torsion bar mounting, every track pin, every wheel bearing. The vehicle represented 2 years of work, countless rejected proposals, and his reputation. If the suspension failed during testing, his career in military vehicle design was finished. Aberdeen Proving Ground, April 1943. Track test course. The testing protocol was brutal. Sustained high-speed runs on paved surfaces, rough terrain courses with obstacles and trenches, endurance tests measuring component wear over hundreds of miles. The Army wanted to break the T-70. If it survived Aberdeen, it might survive combat. If it broke at Aberdeen, American tank crews wouldn't die in flawed vehicles. Initial tests revealed immediate problems. Track shedding occurred during high-speed turns exceeding 35 miles per hour on loose surfaces. The longer unsupported track sections whipped laterally under stress, occasionally jumping off drive sprockets or road wheels. Exactly as critics predicted, the test reports were damning. Excessive track instability at high speeds, combat suitability questionable. Davidson spent sleepless nights reviewing data, recalculating loads, and sketching modifications. The solution emerged from understanding the failure mode. Track shedding occurred because lateral forces during turns exceeded track guide horn capacity. Standard tracks used guides inside the center of each link. Davidson proposed external guides track blocks that prevented lateral movement by engaging the outer edges of road wheels. He flew to Aberdeen, paid for the flight himself, and presented the modification to test engineers. They were skeptical but agreed to try it. Modified tracks arrived within 2 weeks. The T-70 returned to the test course in May 1943. The external guide tracks transformed performance. High-speed turns up to 45 miles per hour showed no shedding. Rough terrain obstacle courses revealed excellent suspension travel. The extended torsion bars absorbed impacts that would have damaged shorter travel systems. Endurance testing demonstrated acceptable wear rates on suspension components. The engineering worked, but opposition within Ordnance remained fierce. The M10 Wolverine tank destroyer was already in production. The M36 Jackson was entering development. Why introduce a third vehicle type with unproven suspension when existing vehicles fulfilled the role adequately? Logistics officers calculated that supporting 3 tank destroyer types increased spare parts inventory by 40%. Maintenance officers worried about training mechanics on unfamiliar suspension systems. General Bruce at Camp Hood reviewed the Aberdeen test reports and recommended limited production. His endorsement carried weight. In September 1943, Ordnance authorized production of 1,000 M18 gun motor carriages. The official designation finally replaced T-70. Delivery to units would begin in summer 1944, just in time for the invasion of France. Davidson remained at Detroit Arsenal, overseeing production and troubleshooting early vehicles. He never served in combat, never commanded troops, never fired the 76mm gun his suspension supported. But his stubbornness, calculations, and willingness to fight bureaucracy for 2 years created a weapon that would change armored warfare doctrine. Production M18s began reaching units in July 1944. The 704th Tank Destroyer Battalion received its vehicles at Camp Hood before deploying to France in August. Crews trained on the new platform, learning its capabilities and limitations. The speed impressed everyone. Top speed exceeded 55 miles per hour on roads faster than any tracked armored vehicle in the world. Cross-country speed exceeded 35 miles per hour on reasonably flat terrain. Acceleration rivaled sports cars. But the armor was thin. Hull front, 12.7 millimeters at 60 degrees. Turret front, 25 millimeters. Barely enough to stop machine gun fire. Certainly insufficient against any German tank or anti-tank gun. Crews understood the trade-off. Speed and gun versus armor. Stay mobile. Shoot first. Never get hit. The 704th deployed to France in late August, attached to 12 Corps of 3rd Army. By September, Patton's advance across France slowed as fuel supplies dwindled and German resistance stiffened. Panthers appeared in growing numbers, rushed from the Eastern Front to stabilize Western defenses. The confrontation between M18s and Panthers was inevitable. September 19th, 1944, 06:30 hours. Arracourt, France. Captain James Leach studied the terrain through binoculars from his M18's cupola. Flat farmland stretched east toward the Marne-Rhine Canal. Morning fog hung close to the ground, reducing visibility to 400 meters. His platoon 6 M18s from Company C, 704th Tank Destroyer Battalion occupied concealed positions in a tree line west of Arracourt. 12 Corps intelligence had warned of German armor concentrations forming for counterattack. Leach's orders: observe, report, engage if necessary. The 113th Panzer Brigade had arrived from southern Germany 2 days earlier. Equipped with 71 Panthers and supporting infantry, the brigade's mission was to halt Patton's advance and recapture Lunéville. German doctrine emphasized the Panthers' superiority in open terrain engagements. Speed and mobility were American problems. German strength lay in firepower and protection. At 0647, Leach's gunner spotted movement through the fog, dark shapes emerging from tree lines 2,000 meters east. Leach counted 15 vehicles. The distinctive profile was unmistakable Panther tanks advancing in staggered column. He grabbed the radio handset. Sabre 3 to Sabre 6, 15 Panthers bearing 090, range 2000, moving west. Over. The battalion commander's response was immediate. Sabre 6 to Sabre 3. Maintain observation. Reinforcements moving to your position. Do not engage without support. Acknowledge. Leach acknowledged and continued watching. The Panthers advanced slowly, perhaps 15 miles per hour, maintaining interval discipline. German tactics favored deliberate movement, using optics to scan for threats before exposing vehicles. The fog helped conceal Leach's position, but it wouldn't last. Sunrise would burn it off within 30 minutes. Standard doctrine called for waiting. M18s lacked the armor to trade shots with Panthers frontally. The 76mm M1A1 gun could penetrate Panther side armor at 800 meters, but frontal armor required closer range and precise shot placement. Engaging 15 Panthers with 6 tank destroyers violated every tactical principle, but Leach recognized the terrain advantage. The Panthers advanced across open ground toward Arracourt. A low ridgeline ran north-south approximately 1,500 meters to the German left flank. If M18s could reach that ridgeline before the Panthers detected them, they could attack from the flank with clear shots at side armor. The question was whether they could cover 1,500 meters, cross rough farmland, and reach firing positions before the Panthers reacted. It required speed, sustained speed, cross-country speed. Everything Davidson's suspension was designed to provide. Leach made his decision. Sabre 3 to all Sabre elements. Follow my movement. Stay spread. Max speed. We're flanking north. 6 M18s erupted from the tree line simultaneously. Engines roared. Tracks bit into soft earth. Acceleration pressed crews back into seats. Leach's speedometer climbed rapidly. 25 miles per hour, 35 miles per hour, 42 miles per hour across uneven farmland. The ride was rough but controlled. Davidson's extended torsion bars absorbed impacts that would have shattered shorter travel suspensions. The 5-wheel configuration, once criticized as inadequate, distributed loads efficiently across longer track sections. German observers spotted the movement immediately. Panthers began traversing turrets left, tracking the American vehicles. Range, 1,000. 800 meters, too far for accurate fire while moving. Panther commanders faced a decision: halt, deploy, and engage at maximum range, or continue advancing toward Arracourt and accept flank exposure. German doctrine emphasized maintaining offensive momentum. The Panthers continued west, increasing speed to 20 miles per hour. Leach's M18s covered 800 meters in 90 seconds. The ridgeline approached rapidly. German machine gun fire began peppering the ground, ranging shots from Panther bowguns. Leach ignored it. At 600 meters from the ridgeline, a Panther's 75mm gun fired. The round impacted 30 meters ahead of Leach's vehicle, throwing dirt and debris. Close, but moving targets at 1,000 meters were difficult even for excellent German gunners. The M18s reached the ridgeline at 06536 minutes after initial contact. Leach's driver braked hard, sliding the vehicle into a hull-down position. The other 5 M18s deployed along the ridge in textbook fashion, spacing themselves to avoid presenting clustered targets. The entire maneuver, from tree line to firing position, covered 1,500 meters in under 6 minutes. Average speed, approximately 50 miles per hour across rough terrain. Panthers now presented perfect flank profiles at ranges from 800 to 1,200 meters. Panther side armor, 40mm at 0 degrees, vulnerable to 76mm fire at this range. Leach acquired the lead Panther in his sight. Gunner, Panther, 11 o'clock, range 900. Identified. Fire. The 76mm gun recoiled. The AP round crossed 900 meters in under 2 seconds. Impact. Mid-hull, Penetration confirmed. The Panther shuddered, slowed, smoke pouring from engine deck. Crew bailed out immediately, 3 men visible, running east. First kill, 0654 hours. The other 5 M18s engaged simultaneously. German return fire was immediate but ineffective. Panthers struggled to traverse turrets while moving. Those that halted to engage presented stationary targets. 3 more Panthers exploded within 30 seconds. Leach's loader rammed another round home. Up. Second engagement. Panther attempting to retreat behind terrain cover. Leach's gunner led the target perfectly. Hit. Rear quarter panel. Penetration. Fire erupted from the engine compartment. The Panther rolled another 20 meters before stopping. Crew didn't evacuate. Second kill, 0655 hours. The engagement lasted 11 minutes. 8 Panthers destroyed, 3 damaged and abandoned, 4 escaped northeast at maximum speed. American casualties. 0. The M18s withdrew west before German artillery could range the ridgeline. By 0705, Leach's platoon had broken contact and returned to assembly areas. After-action reports reached 12 Corps headquarters by noon. The engagement data was extraordinary. 6 M18s had decisively defeated a superior force of Panthers through speed and maneuver alone. The flanking movement covered 1,500 meters in 6 minutes across rough terrain, performance unmatched by any other tracked vehicle in American or German service. The 76mm gun, though less powerful than the Panther's 75mm quad-up K-42, proved adequate when employed against side armor at proper ranges. But the true revelation came from examining the M18 tracks and suspension after the engagement. Maintenance crews inspected every vehicle. 0 track shedding incidents, no broken torsion bars, normal wear rates on road wheels and track pins. The suspension had performed flawlessly, under exactly the conditions critics claimed would cause catastrophic failure. Harley Earl Davidson never knew about Arracourt. Immediately he was 4,000 miles away in Detroit, troubleshooting production issues on later vehicle batches. But the engagement validated every calculation, every stubborn argument, every rejected proposal he'd endured for 2 years. The engineering worked. Combat proved it. The Army would never again question 5-wheel torsion bar suspension. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Berlin, 1942. Waffenamt, German Army Weapons Agency. A technical drawing of the Panzerkampfwagen V Panther covered an engineer's desk. The vehicle represented German armored doctrine at its apex: firepower, protection, and sufficient mobility. Weight, 45 metric tons. Power, 700 horsepower Maybach HL 230 engine. Top speed, 46 km per hour on roads, approximately 28 miles per hour. The Panther could dominate any engagement through superior firepower and armor. Speed was adequate, not exceptional, but sufficient. German engineering philosophy emphasized robust design and overwhelming combat capability. The Panther's suspension used 8 large overlapping road wheels per side, known as schachte Laufwerk interleaved suspension. The design provided excellent cross-country ride quality and distributed weight across maximum track contact area, but it added complexity and weight. Each wheel station required individual mounting. Overlapping wheels trapped mud and debris. Winter conditions froze wheels solid. Maintenance was nightmare. Fuel for German mechanics. The Panther's design reflected strategic assumptions forged on the Eastern Front. Soviet T-34 seconds possessed excellent mobility but inadequate firepower and protection against German guns. Panthers could engage T-34 seconds at ranges exceeding 2,000 meters with near-certain kills. T-34 seconds required closing to 500 meters or less for effective return fire. German doctrine exploited this advantage relentlessly. Engage at maximum range. use superior optics, destroy Soviet armor before it closed distance. This doctrine worked brilliantly in the East. Open steppes provided long sight lines. Panthers operated as mobile strongpoints, anchoring defensive positions and launching limited counteroffensives. Speed mattered less than firepower and protection. Soviet numerical superiority meant German armor fought outnumbered constantly. Survivability took priority over mobility, but Western Front conditions differed fundamentally. American doctrine emphasized mobility and combined arms coordination. American artillery vastly exceeded German capabilities in volume and responsiveness. American air superiority meant daylight movement invited destruction. American industrial capacity produced vehicles faster than Germany could destroy them. The Panther's design advantages firepower and protection mattered less when American forces dictated engagement terms through maneuver. The M18's speed, once dismissed as tactically irrelevant, became decisive in fluid battles, where positioning trumped armor thickness. German crews trained to engage frontally at maximum range found themselves attacked from flanks by vehicles moving faster than Panther turrets could traverse. The irony deepened. German military industry couldn't match American automotive expertise. The Detroit Arsenal, where Davidson worked, represented generations of civilian automotive engineering applied to military problems. American engineers understood suspensions, powertrains, and high-speed dynamics because they'd designed Buicks, Fords, and Chevrolets. German tank designers came from artillery backgrounds, emphasizing guns and armor over automotive refinement. American torsion bar technology, adapted from automotive applications, outperformed German interleaved wheel designs, inherited from World War I-era thinking. The engineering that produced smooth-riding luxury sedans translated directly to tanks that could sustain 50 miles per hour across rough terrain. Germany's engineering excellence in firearms and optics didn't translate to superior automotive engineering. United States Army Technical Intelligence compiled comprehensive Panther analysis in October 1944, based on captured vehicles and combat data. Report findings. Panther suspension provides excellent cross-country ride, but suffers maintenance penalties and weight inefficiency. Interleaved wheel design increases unsprung weight by approximately 25% compared to optimized torsion bar systems. Speed limited by power-to-weight ratio of 15.6 HP/ton. Tactical mobility inferior to American M18 HP/ton, despite superior protection. Panthers protected crews better 80 mm frontal armor versus M18's 12.7 mm. But M18s positioned faster, flanked easier, and withdrew before German guns acquired targets. In static engagements, Panthers won. In mobile warfare, M18s dictated terms. Combat results from Autumn 1944 proved it. Davidson's five-wheel suspension, criticized as structurally unsound, reduced weight while maintaining strength exactly where needed. The engineering wasn't reckless, it was precise. Standard six-wheel designs distributed loads evenly but added unnecessary redundancy. Davidson calculated minimum wheel stations required for structural integrity, then eliminated excess. The weight savings translated directly to speed. The external guide track modification, initially viewed as admitting design failure, actually demonstrated excellent engineering iteration. When testing revealed problems, Davidson identified root causes and implemented targeted solutions rather than abandoning the concept. The modified tracks increased lateral stability without adding significant weight, problem solved through analysis rather than compromise. German industry couldn't produce M18 equivalents even if doctrine demanded them. The Hetzer light tank destroyer achieved 42 km per hour, 26 miles per hour, top speed with 38 mm frontal armor and a 75 mm gun. Faster than Panthers but slower than M18s. More protected than M18s but less mobile. German designs remained trapped between competing requirements, unable to achieve the extreme specialization Davidson's design embraced. The philosophical divide ran deeper. German doctrine viewed tanks as armored fighting vehicles requiring balanced capabilities. American tank destroyer doctrine viewed M18s as self-propelled anti-tank guns requiring only mobility and firepower. Armor protection was irrelevant if crews avoided being hit through speed and positioning. The doctrinal clarity enabled engineering focus. Davidson didn't balance compromises, he eliminated armor to maximize speed. Critics within American Ordnance argued this approach was suicidal. Crews in 12.7mm armored vehicles faced catastrophic casualties if caught by German fire. The criticism was valid in static scenarios, but combat data told different stories. M18 loss rates in 1944 to 1945 remained below M10 Wolverine rates, despite thinner armor. Speed enabled survival. Crews that got hit died, but crews rarely got hit because they controlled engagement geometry. Captured German documents revealed Wehrmacht intelligence consistently underestimated M18 capabilities. Intelligence summaries from Heeresgruppe G in October 1944 described M18s as lightly armored reconnaissance vehicles with inadequate anti-tank capability. The assessment was catastrophically wrong. German units continued engaging M18s as they would armored cars, only to find themselves outflanked by vehicles moving at speeds German doctrine considered impossible for tracked platforms. The misperception imposed costs. German tactical responses remained calibrated for Sherman and M10 speeds. When Panthers deployed to engage reported American armor, they positioned assuming enemy vehicles moved at 25-30 miles per hour maximum. M18s moving at 50 miles per hour rendered those assumptions obsolete. German units repeatedly lost Panthers to flank attacks launched from positions Panthers couldn't reach quickly enough to counter. One Panther crewman, captured after Arracourt, told interrogators, "We saw them moving toward our flank. We increased speed to reposition. They were faster, much faster. By the time we traversed turrets, they were firing into our sides. We couldn't run. We couldn't turn fast enough. We couldn't do anything." The technical analysis was damning for German doctrine. Panther turret traverse rate: 360 degrees in 60 seconds at maximum hydraulic pressure, adequate for engaging frontally or tracking slow-moving targets, inadequate for tracking vehicles crossing the engagement area at 50 miles per hour. Simple geometry. M18 moving perpendicular to Panthers facing at 800 meters range covered approximately 22 meters per second. Panther turret traversed approximately 6 degrees per second. The math didn't favor Germans. Davidson's suspension enabled tactical options German designers never anticipated because German doctrine never valued extreme speed. The engineering reflected doctrinal priorities. German doctrine prioritized survivability and firepower. American tank destroyer doctrine prioritized mobility and responsiveness. Each nation built vehicles matching their doctrine. In Western European terrain with American air superiority and artillery dominance, mobility trumped protection. The irony completed itself when American forces examined captured Panthers after the war. German engineering was excellent: tight tolerances, quality materials, sophisticated designs. But the vehicles were over-engineered for actual combat requirements. Panthers were masterpieces solving problems that mattered on the Eastern Front but became liabilities in the West. M18s were deliberately under-engineered, optimizing the single characteristic that mattered most: speed. By December 1944, Wehrmacht tactical guidance explicitly warned against engaging M18s in open terrain without numerical superiority or prepared positions. The warning acknowledged reality. Panthers dominated static engagements. M18s dominated mobile warfare. In late war conditions where Allied air superiority prevented German daylight movement and Allied artillery dominated prepared positions, mobile warfare became the only sustainable option. German industry never adapted. Panther production continued with minor modifications but no fundamental redesign. The suspension remained complex and heavy. Top speed never exceeded 46 kph. German doctrine, forged in Eastern victories, couldn't evolve quickly enough to meet Western challenges. The institutional inertia that made German armoured forces dominant in 1941 to 1942 became a vulnerability by 1944 to 1945. One civilian engineer in Detroit, working with slide rules and stress calculations, produced a vehicle that tactical doctrine hadn't fully envisioned. His stubbornness overrode institutional resistance. His calculations proved correct under combat conditions critics said would cause failure. The five-wheel suspension, declared unsound by Army Ordnance in 1942, became standard reference for post-war light armour development. The combat data was irrefutable. The engineering was sound. The doctrine was validated. And somewhere in Berlin, German intelligence officers compiled reports explaining how American tank destroyers they'd dismissed as inadequate were systematically hunting Panthers across France. October 1944 through January 1945. 3rd Army Headquarters, Nancy, France. A stack of after-action reports covered Major General Walton Walker's desk. 12. Corps had compiled engagement data from every M18 unit operating in the Lorraine campaign. The statistics told a story that contradicted 2 decades of armoured warfare theory. Tank destroyers weren't supposed to hunt tanks, they were supposed to defend against them. Yet M18s were actively seeking combat with German armour and winning consistently. Walker's operations officer, Colonel Hammond Pierce, prepared a summary memorandum for Lieutenant General George S. Patton. The document synthesized tactical lessons from September through October 1944. Key findings. M18 units achieved kill-loss ratios of 4:1 against German armour, significantly exceeding ratios for M10, Wolverines 2.3:1, and Sherman tanks 1:8:1. The differential wasn't firepower. All 3 vehicles mounted guns capable of defeating German armour under proper conditions. The differential was speed. M18 units executed flanking manoeuvres that other American armour couldn't attempt. They reached positions faster, withdrew from danger quicker, and exploited breakthrough opportunities that vanished before heavier vehicles arrived. Speed translated directly to tactical options. More options meant better engagement geometry. Better geometry meant more kills and fewer losses. Patton read Pierce's memo on October 28. His marginal notes were characteristically blunt. "Why the hell don't we have more of these? Get Ordnance on the phone." By November 2, Patton had submitted formal requests to European Theatre Headquarters for additional M18 battalions. The request cited specific engagements, statistical analysis, and tactical assessments from corps and division commanders. But production had already peaked. The original September 1943 contract authorized 1,000 M18s. By October 1944, approximately 800 had been delivered. Army ground forces, responsible for equipment allocation, had already committed to M36 Jackson production as the primary tank destroyer for 1,945 operations. The M36 mounted a 90mm gun more powerful than the M18's 76mm and provided better armour protection. On paper, the M36 was superior. Theatre commanders disagreed. The 90mm gun's additional penetration mattered less than the M18's speed in actual combat conditions. M36s, built on Sherman chassis, topped out at 30 miles per hour. They couldn't execute the high-speed flanking maneuvers that made M18s so effective. Firepower didn't compensate for reduced mobility. The bureaucratic fight intensified through November. Army ground forces cited standardization concerns supporting multiple tank destroyer types, complicated logistics. Theatre commanders cited combat effectiveness. Soldiers preferred vehicles that kept them alive. Equipment allocation boards in Washington reviewed deployment data, loss reports, and commander testimonials. Meanwhile, frontline units developed tactics exploiting M18 capabilities. The 704th Tank Destroyer Battalion refined techniques pioneered at Arracourt. Standard procedure. reconnaissance elements identified German armor positions. M18 platoons conducted high-speed approach marches using terrain masking, executed coordinated flank attacks from multiple directions, then withdrew before German forces could mass counterfire. The tactics required precise timing and coordination. Radio discipline was critical. Platoon leaders needed to read terrain quickly, identifying routes that balanced speed with concealment. Drivers needed skill to maintain formation at high speeds across rough ground. Gunners needed to engage effectively from moving platforms difficult but trainable. Training guidance circulated through tank destroyer command channels. The Tank Destroyer School at Camp Hood, Texas, received detailed after-action reports from European theater units. Instructors modified curricula to emphasize high-speed maneuver tactics. New M18 crews arriving in theater came with better preparation for the vehicle's unique capabilities. By December 1944, M18 battalions operated with refined doctrine that bore little resemblance to original tank destroyer concepts. The 1941 doctrine envisioned tank destroyers as mobile reserves responding to armored breakthroughs, essentially defensive weapons. 1944 reality saw M18s conducting offensive operations, hunting German armor proactively, and functioning as exploitation forces during breakthrough operations. The transformation wasn't limited to tactics. Maintenance procedures evolved to support sustained high-speed operations. Davidson's 5-wheel suspension, though mechanically sound, required different maintenance approaches than 6-wheel systems. Track tension settings were critical. Too tight caused excessive wear, too loose risked shedding during high-speed turns. Ordnance companies developed standardized adjustment procedures and trained mechanics on proper tensioning techniques. Spare parts logistics adapted to combat usage patterns. Initial parts allocation assumed M18s would operate similarly to M10s. Reality showed different failure modes and wear patterns. Track pins wore faster due to higher operating speeds. Torsion bars occasionally cracked under sustained rough terrain operations, not design failures, but predictable wear items requiring replacement. Supply officers adjusted inventory accordingly. The institutional learning curve was steep but effective. Problems identified in September had solutions by December. Crews developed expertise. Maintenance teams gained proficiency. Tactical doctrine matured. The M18 evolved from experimental vehicle to proven combat system in 4 months. Recognition came officially in January 1945. The War Department published Training Circular 45, Employment of M18 Gun Motor Carriage. The document synthesized lessons learned from 6 months of combat operations. Key sections addressed high-speed maneuver tactics, engagement geometry optimization, and coordination with other arms. The circular became required reading for all armor and tank destroyer officers. Harley Earl Davidson received formal recognition in November 1944 when Army Ordnance awarded him the Certificate of Appreciation for Outstanding Civilian Service. The citation noted his innovative suspension design, enabling unprecedented tactical mobility in armored warfare. Davidson attended a brief ceremony at Detroit Arsenal, accepted the certificate, and returned to work. He never sought publicity. Engineering problems interested him more than ceremonies. But within Army Ordnance, Davidson's vindication was complete. Officers who'd opposed the 5-wheel suspension in 1942 now championed it. Technical reports praised its efficiency and effectiveness. Post-war vehicle development programs incorporated lessons learned from M18 design. The institutional resistance that nearly killed the program transformed into enthusiastic endorsement once combat validated the engineering. The Medal of Honor never came. Davidson wasn't a soldier and never faced enemy fire. But his contribution to tactical capability was measurable and significant. Estimates from Ordnance Department analysis suggested M18s destroyed approximately 500 German armored vehicles between July 1944 and May 1945, while suffering losses of fewer than 100 vehicles. The favorable exchange ratio directly resulted from speed advantages Davidson's suspension enabled. Combat reports circulated beyond armored warfare circles. Infantry commanders learned that M18s could respond to armor threats faster than any other American vehicle. Artillery officers coordinated fires to suppress German anti-tank weapons while M18s maneuvered. Air liaison officers directed close air support to enable M18 exploitation of breakthroughs. The vehicle's speed enabled combined arms integration that slower platforms couldn't match. German intelligence archives, captured after the war, revealed Wehrmacht awareness of M18 capabilities by late 1944. A December intelligence summary from OB West Oberbefehlshaber West, Commander-in-Chief West, described M18s as Hochgeschwindigkeit, Jagdpanzer, high-speed tank hunters, and recommended avoiding engagement in open terrain. The warning came too late to influence German equipment development but demonstrated that Allied tactical mobility had become a recognized threat. By January 1945, production of the full 1000 M18C was nearly complete. No additional contracts followed. Army Ground Forces had committed to M36 production for 1,945 to 1,946. But the 1000 M18s built proved sufficient for theatre requirements. Multiple battalions deployed across European and Pacific theatres. Each achieved notable success ratios. The vehicle's reputation solidified. Fastest tracked vehicle in the war, effective tank killer, and vindication of radical engineering. The publicity value wasn't lost on Army public relations. War bond drives featured M18s in promotional materials. Newsreels showed the vehicles in action, carefully edited footage of high-speed maneuvers and firing demonstrations. The narrative emphasized American technological innovation and superiority. "Our boys have the fastest armor in the world," became a recruiting tagline. But the soldiers who crewed M18s understood the reality behind the publicity. Speed kept them alive, but thin armor meant no room for error. One hit usually proved fatal. Crews accepted the trade-off because they controlled engagement terms. If they used speed properly, they rarely got hit. If they made mistakes, consequences were immediate and catastrophic. The psychological dynamic differed markedly from Sherman or M10 crews. Heavier armor created false confidence. Crews believed they could absorb hits and survive. M18 crews had no such illusions. They knew every engagement was binary: kill the enemy quickly or die. The awareness bred caution, precision, and aggressive use of terrain. Paradoxically, the lack of armor protection created tactical discipline that improved survival rates. Training emphasized this. Psychology. Instructors at Camp Hood told new crews, "Your armor is your speed. The moment you stop moving, you're a target. Keep moving, use terrain, shoot and scoot. The German can't kill what he can't hit, and he can't hit what moves at 50 miles per hour." The doctrine worked because it aligned engineering with tactics, with training. Davidson's suspension enabled the speed. Tactical doctrine exploited the speed. Training prepared crews to use speed effectively. The system functioned as an integrated whole. Remove any component, and effectiveness declined. By war's end, the M18 had proven itself conclusively. Combat data showed superior performance in mobile warfare conditions. Tactical lessons shaped post-war armored warfare doctrine. Engineering innovations influenced vehicle development for decades. One civilian engineer's stubbornness, fighting institutional resistance for 2 years, produced measurable strategic impact. February 1945 through May 1945. The Rhineland to Bavaria. As Allied armies crossed the Rhine and drove into Germany's industrial heartland, M18s adapted to changing operational conditions. The open terrain of France gave way to forests, villages, and river valleys. High-speed flanking maneuvers became less frequent. Close-quarters combat increased. The tactical environment that favored M18s in autumn 1944 shifted toward infantry-armor cooperation in restrictive terrain. Yet M18 units maintained effectiveness by adapting tactics to conditions. In urban areas, speed-enabled rapid position changes fire from one location, relocate before German forces could respond, engage from a new position. The lightweight allowed M18s to cross bridges that couldn't support heavier armor. The compact turret traversed 360 degrees manually in 20 seconds, enabled quick target engagement in close quarters. Statistical summaries from 1st and 3rd Armies showed M18 loss rates remained consistently below other tank destroyers through war's end. The 704th Tank Destroyer Battalion, which pioneered M18 tactics at Arracourt, finished the war with 127 confirmed German armoured vehicle kills against 19 M18s lost in combat, a 6-7-1 ratio. Other M18 battalions achieved similar results. The Pacific Theatre told a different story. M18s, deployed to the Philippines in early 1945, encountered terrain and tactical conditions vastly different from Europe. Dense jungle limited high-speed operations. Japanese armor was lighter and less capable than German vehicles. The M18's speed advantages mattered less when maximum engagement ranges rarely exceeded 200 meters, but even in unsuitable terrain, M18s proved valuable in exploitation roles. During the liberation of Luzon, M18 units functioned as mobile fire support, engaging Japanese strongpoints and bunkers with direct fire. The 76mm gun's high explosive rounds were effective against fortifications. Mobility enabled rapid redeployment to support infantry advances across multiple sectors. By May 1945, Germany's surrender ended the European War. M18s participating in final operations against scattered German resistance validated their role one last time. Near Berchtesgaden, an M18 platoon from the 827th Tank Destroyer Battalion destroyed 3 Tiger II tanks attempting to block a mountain pass. The engagement demonstrated that even against the most heavily armoured German tanks, properly employed M18s could achieve success through manoeuvre and flank shots. Post-war analysis by Army Ordnance compiled comprehensive M18 performance data. Total M18 production, 2,507 vehicles. The original contract was expanded based on combat success. Total confirmed German armoured vehicle kills, approximately 526. Total M18s lost to all causes, approximately 216. Overall exchange ratio, 2.4-1 against German armour, better than any other American armoured vehicle type. The data vindicated every controversial design decision Davidson made. The 5-wheel suspension performed reliably across hundreds of thousands of operational miles. Track shedding incidents occurred at rates comparable to conventional suspensions. Torsion bar failures remained within acceptable tolerances. Maintenance requirements were actually lower than 6-wheel systems due to fewer components. Speed records spoke for themselves. The M18 remained the fastest tracked vehicle in World War II. No German, British, or Soviet vehicle matched its combination of speed and firepower. The Cromwell tank approached M18 speeds but mounted a less powerful gun. Soviet light tanks achieved high speeds but lacked armor and firepower. Only the M18 integrated extreme speed with adequate anti-tank capability. But the post-war army faced different requirements. Atomic weapons and Cold War strategic considerations emphasized armor protection against nuclear effects. Speed mattered less than survivability. The M18's thin armor, acceptable in World War II mobile warfare, seemed inadequate for hypothetical nuclear battlefields. Development priorities shifted toward heavier, better protected vehicles. The M18 was retired from active service by 1953. Remaining vehicles went to National Guard units or foreign military assistance programs. Some served with Allied nations through the 1,960 seconds. The vehicle that dominated 1,944 to 1,945 tactical mobility faded into obsolescence as doctrine evolved. Yet Davidson's engineering principles endured. The 5-wheel torsion bar suspension influenced post-war light armor development. The M41 Walker Bulldog light tank, developed in the late 1940s, incorporated torsion bar suspension with extended travel similar to Davidson's design. The M551 Sheridan, developed in the 1960s, used torsion bars and emphasized mobility over protection, direct descendants of M18 design philosophy. Soviet designers studied captured M18s after the war. The ASU-85 airborne assault gun, developed in the 1950s, showed clear influence from M18 concepts: light armor, powerful gun, emphasis on mobility. The engineering lesson oft crossed ideological boundaries because the physics remained universal. In Korea, some M18s saw limited service with Republic of Korea Army units. The terrain and tactical conditions differed from Europe, but the vehicles performed adequately in mobile operations. By Vietnam, M18s were obsolete, replaced by more modern vehicles. But veterans who'd crewed them remembered the speed, the vulnerability, and the tactical flexibility that kept them alive. Academic analysis of armored warfare evolution identified the M18 as a pivotal case study. Military theorists examining the relationship between mobility and protection used M18 combat data to illustrate how tactical doctrine could prioritize one attribute at the expense of others and still achieve success. The vehicle became a reference point in debates about balanced versus specialized design philosophy. Engineering schools taught Davidson's suspension as an example of innovative problem-solving under constraints. The design brief seemed impossible to achieve 50-plus MPH speeds in a 20-ton tracked vehicle. Davidson solved it by questioning assumptions and eliminating unnecessary components. The case study appeared in mechanical engineering curricula at MIT, Purdue, and other institutions. By the 1960s, Harley Earl Davidson had retired from automotive engineering. He lived quietly in suburban Detroit, occasionally consulting on suspension projects, but mostly tending his garden and reading technical journals. Journalists occasionally found him for interviews about the M18. His responses were characteristically terse. "I did the math. The math was correct. The Army eventually agreed." He never expressed bitterness about the 2-year struggle to get the design approved. When asked if the institutional resistance frustrated him, he shrugged. "Engineers don't make decisions. Generals make decisions. My job was providing data so they could decide correctly. Eventually, they did." Davidson died in 1967 at age 68. His obituary in the Detroit Free Press mentioned his work on the M18, but focused more on his automotive engineering career. Few readers understood the significance of his World War II contribution. The suspension design that changed armored warfare tactics was a footnote in a life dedicated to solving engineering problems. United States Army Ordnance Museum, Aberdeen Proving Ground, Maryland, 1982. An M18 Hellcat sat on display in the World War II armored vehicle section. The placard read, "M18 gun motor carriage, fastest tracked vehicle of World War II, top speed, 55 miles per hour, crew. 5. Armament, 76mm M1A1 gun, production, 2,507 vehicles. Service, 1,944 to 1,953. The description was accurate but incomplete. It mentioned specifications, but not the engineering struggle behind them. It noted speed, but not the tactical revolution that speed enabled. It listed production numbers, but not the combat effectiveness those vehicles achieved. Museum visitors, mostly military families and history enthusiasts, paused briefly before the M18. Most found the Sherman tanks more interesting familiar from films and photographs. The M18 was obscure, a footnote in popular memory. Yet for armored warfare professionals and military historians, the vehicle represented a crucial lesson. Extreme specialization, when aligned with proper doctrine, could outperform balanced designs. The Army's Armour School at Fort Knox used M18 case studies in officer education. Tactical instruction examined Arracourt and similar engagements to illustrate mobility's role in combined arms operations. The engineering story, Davidson's struggle against institutional resistance, appeared in leadership courses as an example of how innovation required persistence against bureaucratic inertia. By the 1992, only a handful of operational M18s remained worldwide. Most resided in museums or private collections. Veteran organizations occasionally gathered former M18 crewmen for reunions. These gatherings grew smaller each year as the World War II generation aged. Men who'd raced across France at 50 miles per hour, hunted panthers in the Ardennes, and survived by speed rather than armor, shared memories that seemed increasingly remote to younger generations. James Leach, who'd commanded the Arracourt engagement, attended reunions until his death in 1994. In a 1989 interview with Army magazine, he reflected on the M18. "We knew we were driving around in a tin can, one hit and you were done. But that speed, nothing else moved like that. If you used it right, you controlled the fight. The German had to react to you instead of the other way around. That's how you survived." The tactical insight was profound. In armored warfare, controlling engagement geometry often mattered more than firepower or protection. The side that chose when, where, and how to fight gained decisive advantages. The M18's speed provided that control. Crews who understood this principle survived and succeeded. Those who didn't often died quickly. Archival research in the 1992s and 2000s uncovered additional details about M18 development and Davidson's role. The National Archives held complete design files, correspondence between Davidson and Army Ordnance, test reports from Aberdeen, and combat after-action reports. Historians piecing together the story found a narrative more compelling than they'd expected. Davidson wasn't a celebrated figure. No Congressional Medal of Honor, no ticker-tape parades, no best-selling memoirs. Just an engineer who solved a problem, fought bureaucracy, and proved his calculations correct. The humility and professionalism resonated. In an era of manufactured celebrity, Davidson's quiet competence seemed refreshing. Military vehicle collectors prized M18s. Restoration projects brought survivors back to running condition. Demonstration runs at military vehicle shows allowed spectators to see the speed that made the vehicle legendary. The sight of a 20-ton tracked vehicle, accelerating to highway speeds, tracks churning, engine roaring, captured imaginations. This was the vehicle that hunted panthers and won. Academic papers analyzing World War II armored warfare consistently cited M18 statistics. The exchange ratios, the speed records, the tactical innovations, all served as data points in larger arguments about weapon system design and tactical doctrine. The M18 became a case study precisely because it was an outlier. Most vehicles balanced competing requirements. The M18 didn't. It specialized radically, and that specialization worked. Comparative analysis with other nations' vehicles highlighted American automotive engineering expertise. German, Soviet, and British designers produced excellent armored vehicles, but none matched American capabilities in high-speed tracked vehicle design. The engineering that produced Buicks and Chevrolets translated directly to military applications. Detroit's automotive expertise became strategic advantage. The Fort Knox Patton Museum displayed the 704th Tank Destroyer Battalion's actual M18 from Arracourt, preserved with original markings and combat damage. A dent in the hull side showed where a German 7.92mm machine gun round had struck but failed to penetrate. The vehicle sat as physical testament to engagements that validated Davidson's engineering and revolutionary tactical employment. By 2010, digital archives made primary sources accessible online. Researchers worldwide could access Davidson's original design drawings, Army Ordnance correspondence, test reports, and combat records. The democratization of historical research brought renewed interest. Blog posts, YouTube videos, and online forums, discussed M18 technical details and combat performance. A new generation discovered the vehicle's story. Veterans' oral history projects captured final testimonies from surviving M18 crewmen. The recordings preserved voices, describing what 55 miles per hour felt like in a tracked vehicle, how quickly terrain features approached, the skill required to maintain formation at high speed, the terror and exhilaration of hunting panthers. These first-hand accounts added human dimension to statistical records. The last known M18 combat veteran, former Corporal Robert Henderson, died in 2018 at age 96. His obituary mentioned his World War II service, but not specifically his M18 crew position. The living connection to the vehicle's combat history ended. Only archival records, preserved vehicles, and historical analysis remained. Modern military vehicle designers occasionally reference the M18 when discussing mobility versus protection trade-offs. The Striker family of vehicles, emphasizing speed and deployability over armor, echoes M18 philosophy. Contemporary debates about light versus heavy armor for rapid deployment forces parallel discussions from 1942 about tank destroyer design. The fundamental questions remain: how much protection is necessary? What speed is sufficient? Where should design prioritize capabilities? Davidson's answer: prioritize mobility radically, minimize protection to essential levels, maintain adequate firepower worked because tactical doctrine supported it. The lesson for modern designers: specialized vehicles require specialized doctrine. Build an M18 equivalent, but employ it like a heavy tank, and it fails. Employ it correctly, and it revolutionizes tactics. The M18's place in military history is secure, though not prominent. It lacks the iconic status of Sherman tanks or the dramatic reputation of German Tigers, but for professionals studying armored warfare evolution, the M18 represents a crucial inflection point, the moment when mobility as a primary characteristic enabled tactical success against better protected opponents. Harley Earl Davidson's legacy lives in suspension designs, tactical doctrine, and the principle that persistent engineering, backed by solid mathematics, can overcome institutional resistance. His stubbornness changed how armies employed light armor. His calculations proved correct under the harshest test combat. His contribution to Allied victory was measurable. Approximately 526 German armored vehicles destroyed by M18s, thousands of American lives saved by speed that kept crews alive. The five-wheel torsion bar suspension, declared unsound in 1942, became a reference design for post-war light armor. The tactical employment, considered suicidal by critics, achieved the best exchange ratios of any American armored vehicle. The engineering that Army Ordnance nearly rejected proved decisive on battlefields from France to Bavaria. 78 years after Arracourt, an M18 at the Bovington Tank Museum in England still bears original markings from the 704th Tank Destroyer Battalion. Visitors pause, read the placard, perhaps watch video footage of the vehicle in motion. Most move on quickly, drawn to more famous exhibits. But occasionally someone studies the suspension, counts the road wheels, notes the spacing, and asks the guide, why only 5 wheels? Every other tank has 6 or more. The guide, if knowledgeable, explains Davidson's design, the weight reduction, the speed advantages, the combat effectiveness. The visitor nods, understanding dawning. This odd-looking vehicle with thin armor and strange suspension hunted panthers successfully because an engineer refused to accept conventional wisdom. That refusal, sustained through 2 years of opposition, changed armored warfare. One engineer's calculations, validated by combat, shaped doctrine for decades. The story deserves remembering not because it's dramatic, though Arracourt provided drama enough, but because it illustrates how persistent problem-solving, even in the face of institutional resistance, can alter strategic outcomes. The M18 Hellcat, fastest tracked vehicle of World War II, proven tank killer, and monument to an engineer who did the math, trusted the math, and convinced an army to build what the math promised. 78 minutes of combat at Arracourt validated 2 years of engineering struggle. 526 German armored vehicles destroyed validated radical design specialization. Survival of thousands of American crewmen validated the principle that speed, properly employed, protects better than armor plate. Harley Earl Davidson's name appears on the original design documents preserved at the National Archives. His signature authorized each design change, each test modification, each production specification. The paperwork remains, yellowed but legible, physical evidence of engineering that changed warfare. The documents don't describe a hero. They describe an engineer who solved a problem, proved the solution worked, and moved on to the next problem. That quiet professionalism, more than speed records or kill ratios, may be Davidson's most lasting legacy. Innovation doesn't require genius or drama. It requires competence, persistence, and willingness to trust calculations over intuition. Davidson possessed all three. The M18 proved it. History remembers accordingly. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.